Okay, so back to chemistry. So for the next chunk of this unit, we're going to talk about specific categories of liquids instead of like all liquids. And these are our acids and bases. This is 6.4. Acids and bases are actually very ancient categorizations. From quite a long time ago, human beings have sort of been collecting information about the world around us, and we've been categorizing liquids into these two different categories since almost before we have written records. It's a very, very old system of classification, where we decided that acids are things that are sour, they sting the skin, they're kind of watery in texture, and they're conductive to electricity. So this includes things like vinegar, lemon juice, stomach acid, even some things that we drink like some soda pops and teas and stuff like that are a little bit acidic. Bases, on the other hand, are bitter to taste. They sting as well, they can burn your skin. They're slippery, feel sort of soapy, and also conductive to electricity. So this includes soaps, lye, bleach, ammonia, baking soda. There's some other stuff that we might use in our household stuff that counts as bases. And what we've learned is that bases and acids are kind of opposites. Not so much that they have opposite traits, because not all their traits are opposite one another, but in that they neutralize one another. If you mix an acid and a base together, you can end up with something that's neither an acid or a base. It'll lose those properties. And so that's sort of the underpinning behind this categorization. Water is actually kind of an odd case. Sometimes it acts like an acid in chemical reactions, and sometimes it acts like a base. And we're going to talk about why when we're talking about our acid-base theories. So we've had these groups of chemicals. Both are large groups. There's lots of different acids and lots of different bases. Long before we had any idea what might be sort of the cause behind them, what part of the molecule makes an acid or makes a base. And so trying to come up with a chemical understanding behind it turned out to be really difficult. And at this point, we actually still have 3 different acid-base theories that can be applied, sort of depending on what you're trying to achieve. So we're going to go through these 3 theories. Number 1, Arrhenius acids and bases. With an Arrhenius acid, the acid releases H+ ions into water when you mix it with water. An H+ ion is hydrogen ion that's lost its lone electron, and it basically just leaves a proton. And so this is one of the few ways that you can get sort of free-range protons. Usually protons are tightly bounded up into the nuclei of the atoms. They don't actually get out and do much, but they can become just an individual proton in water when it's an acid. Bases, on the other hand, release hydroxide ions, the OH- group, when in water. And so if we have an H and we add an OH, we get H2O. So an acid plus a base, from this definition, makes water, plus a salt, the leftovers. So if we had like HCl plus NaOH, we would take the NaCl would be our leftover. That's actually just table salt. But it's not always table salt. There's lots of different ionic compounds that can form this way. With this definition, you can tell just by looking whether or not you have acids and bases. If HCl has an H on it, it can be an acid. NaOH has an OH on it, it can be a base. But it excludes a lot of things that have the right properties, like ammonia, for example, is NH3. And it's a base, which doesn't make sense because it doesn't have that OH group. So it's a bit too narrow. We have sort of a Goldilocks situation going on here. The Arrhenius works very well for a very narrow group of acids and bases, but it leaves out a lot of things that are otherwise classified as acids and bases because they don't fit the pattern quite right. Okay, Bronsted-Lowry acids and bases. With Bronsted-Lowry acids and bases, we still are looking at the H+ ions. The acids are donators and the bases are acceptors. So one of them's losing an H and the other one is gaining an H. And we can kind of track where they're going. Each acid is paired up with the conjugate base, which is its form after it's lost its H. So HNO2 here becomes just NO2. And so on the diagrams we draw the linking arrow to show this is sort of before and after, acid to conjugate base. Then the one that gained the H has a conjugate acid, so H2O becomes H3O. And so we're really just tracking the H's. Where are they going? Who lost an H and who gained an H determines the acid and the base. Each base has a conjugate acid that forms. Because these are reversible reactions, if they're going the other direction, this one's the acid and this one's the base. And in the past, I've given out like sheets of problems where you'd have just a bunch of these and you draw your arrows and label and stuff like that. It didn't work out very well with the Google Forms, and so we're skipping that. But I did want to go through this a little bit. Instead, it's more like just understanding our definitions. Okay, so this one's a really useful definition. It includes most everything that we consider an acid, and it doesn't include a whole lot of things that we don't consider acids and bases. Lewis acids and bases, instead of looking at H's, decided to focus on electrons. This is the same Lewis who did the Lewis diagrams of electrons, and so he was sort of just obsessed. In this case, acids are acceptors. They accept a pair of electrons, and bases are donors. They donate a pair of electrons. And they form what's called a coordinate covalent bond and a single new compound. Coordinate covalent bonds occur where instead of sharing electrons, one compound is just straight up giving, or well, one compound is the source for both electrons in the bond. Instead of, usually we saw it where each compound in the bond gave one electron to form the bond. So NH3 plus H plus becomes NH4. The NH3 is the donator, and the H plus is the acceptor. We can tell this by looking because H plus as a positively charged ion does not have any electrons on it, and so it couldn't be a donator. So this is the base, this one's the acid, and they make a single NH4 plus compound. This works really well. It's very inclusive, but there's lots of other things that do this that don't have quite the right properties. That they act the same way, but we don't technically consider them acids and bases because they aren't sour or bitter. You know, they don't have the right other properties. And so this might be considered too wide of a definition. So we have sort of a Goldilocks problem. Too narrow, too wide, just right. So we usually are referring to Bronsted-Lowry acids and bases. Okay, so that's it for the notes. That was a lot about acids and bases. Next time we'll talk about pH and the pH scale and how to calculate pH. But today there's no math, so hooray, no math. Have a great day.